Hello, welcome back. Few things before starting on this. I'm not going to mention the numbers of the lessons. That's one thing. I'm not sure what the number is going to be in the end, but I know where we are. So that's one of the things. Um, there are a few pending questions that I wanted to give answers to from before. Not the last one, but the one before that. I left a few questions open, and I'll answer one of them now, or sort of give an answer. And the question was, if you recall, the question was, why are all these statements errors? And so on. It doesn't matter what you do. And you'll notice that the error indicator, this little error thing, is pointing always at the use of IP directly. And in fact, there are no instructions that I know of where you can actually use this value as a parameter. Maybe there are, not that I know of. My answer, I guess, would be that in a way that this doesn't really make any sense. It's like asking a question that the processor can't answer. The instruction pointer is the place where the processor retrieves the next instruction. And this itself is an instruction. So it's kind of like asking it to do two things at once. If it reads this in and starts decoding the instruction, then this has to change. So this is kind of like an almost meaningless question. What this is really asking is, what is IP as long as you don't process this instruction? And that's kind of meaningless. However, IP does move around, and you can set this IP, but not in this way. There are prescribed ways of setting this IP value. One of them is exactly equal to this, equivalent to this one. This removes from the stack the number and puts that number, whatever it is, into IP. So this is the prescribed way of altering IP. Other ones, probably nobody has a problem with this instruction. Everybody understands that, or call. All of these special instructions are ways of altering the flow of execution of the program. And that's the only interface to changing this thing. We understand that these are actually special, have special meanings. This move instruction on its own cannot leave this value unaltered. So you're not allowed to do that. It's just not wired that way. And you're not allowed, even though these two, if this were allowed, that would have the same result as this. You're not allowed to use this, whatever circuitry executes this pop. It's not the same circuitry that will execute this ret. And even though the answer would come out the same and everything would end up the same, the processor won't allow you to do it. Another thing I could add to that is that as the processor, as the CPU is moving along, it's actually looking ahead and decoding instructions in its path, and so it can use the fact that these are special calls or special operations to make predictions and guess what's going to happen next. It might see this. It'll see this call 256 and fetch code from there and start the process of decoding even while this is going on, so that when it gets here, if this happens to happen, in this case there's no condition, so it will happen, it's ready to quickly execute that code. So that's partly the answer to that. The other thing that I left hanging in the air had to do with these. Hang on a second. The calling convention. I've been through this already, and I didn't upload my previous version. I realized that I spent so much time typing in these things that most of the time is just spent watching me try to type in these things. So I prepared a little text file. Oh, that's the other thing. You'll notice from now on I've changed the format of this. I don't know why. This happens to be the format of the old DOS directory listings, with the file names are on the left. It's this way, so I guess for authenticity I'll change that. Yeah, I've got it in here. Call conventions. And the question I was giving was why certain ways of calling might perhaps have advantages, or one way might have an advantage over another. Or not. And anyway, so I made this table so you don't have to watch me typing it all in. And what I've got here, this came from Wikipedia, by the way. You can look it up yourself. Their table is more extensive. Here's the name of the convention. These are just agreements that people decided on. These are the different ways that people have decided to use their call. This part is built into the machine. This part is just what people agreed on. People have agreed to do this. So one of them is called Pascal. Cleanup responsibility means who resets the stack pointer. Callee means the person called. I should mention that. The one that's like the 200s in our account. Okay, so the callee is the function, the being called, and where the call is issued is called the caller. The function wherein the call is issued is called the caller. And then there's the order of pushing the arguments on the stack. Either it's left or right, sometimes none. None here just indicates that it might use registers or some other way. Instead of using the stack, you don't have to use the stack. You don't want to. And that's it. So there are several ones that are on that list there. One is called Pascal, I mentioned already. Fast call sometimes doesn't use any pushing for popping. So left to right. Left to right. That's the normal way that you read. So that means that the function foo this is why in the table. If you have a function foo like that, and it has 3 parameters, the order of the push, left to right, means this first, then this, and then this. Otherwise, backward. That's all. Okay. So I split these up into callee and caller, groups. So these are all the callee versions, and these ones are the caller ones. C decal is C or C++, which happens to be right to left. So they push through. Syscall is, I don't know if you've ever heard of it before. Off length, I have no idea. But that's different from C decal. Even though the caller cleans up, it pushes left to right. And the last one here in this small list is something sort of specific for C++, this call, which could be either one or the other, it turns out. And the order is backwards, right to left. Now, I've printed out the code that corresponding to these different mixtures of callee, caller, right to left, left to right. For the example above, foo. So here's an example of a left to right caller response, caller cleanup call. So left to right pushes 1, 2, 3, call, clean out. And here's the left to right with no cleanup. Nothing happens. Just returns there. And here is the stack for the caller at the point of the foo is entered. So sitting on the stack, when foo gets entered, the variables in this order. The last thing pushed was 3, so the 3 is last first, essentially, in memory. In terms of memory order, you would see the 3 first if you're reading increasing address. And you see that these two are identical. There's no difference here in terms of what the foo sees on the stack. So what's my comment here? So all of the arguments are pushed in the normal order, that they end up in reversed order on the stack, because the stack grows down. And an example, for example, 2 appears in memory after 3. If you had a pointer to memory, it appears in memory. But you're going to see the 3 in the next byte or word or whatever will be a 2. Backward. Okay. Now the leave code if the caller is responsible for cleaning up, call this column is caller responsibility. It's just the one we saw already. And if the callee is responsible, it's this. And this ref is a special ref. I was trying to figure out how you can do a return and fix up the stack at the same time. And I thought probably there's a special type of return call. And in fact, that's true. I'll show you before going on to the next group where I found that out. You can download this file. I'll try and find the URL again. dots. Oh, it's a little bit too authentic. Okay, well, maybe I can get out of this mode. No, I do that. Maybe I can just turn that back to normal. There. This is the normal view. This here is basically a text file, and that's where I found out about this stuff. And it lists all of the Intel instructions. So if you go and download this thing, you can actually have a look through and see all of the instructions. The one I was interested in was ret. Ret. Forgetting about this F bit. And this transfers control from procedure back to the address, the one on the stack. And then this n bytes thing is an optional number which will release from the stack, which means it's going to increment the stack pointer either during or just after the instruction is complete. And so that's what that means. Okay, now I'm probably taking too long again, but other times it took even longer. Now, the other case is if the pushing is from right to left, that's backwards. So if there are calls, push backwards, call, clean up, sorry, caller clean up, callie clean up, and here's the stack. This is the one you would see in a C program on the left here. In fact, again, they're exactly the same, except as you can see, these numbers are now ordered in the way you would see them in the argument list for the function. In memory, they're in the same order as they're listed. And the lead code is exactly the same as before. No difference in that, and you wouldn't expect it. So, that's all the types, the conventions and columns. Actually, more, but that's all the important cases. Now, I had a little question at the end here. For C, the combination is backwards pushing, caller, responsibility. And there's something that enables, which either you know it now, and so it's, already know it. If you don't know it, it's an interesting little puzzle. So I thought I'd leave for you a puzzle, and I'm going to answer it right now instead of waiting 2 tutorials. So what I'm going to ask, and then you can hit pause and try to figure it out, is there's something special about this combination that makes there's something that you can do with this combination of RTL and caller that you can't do with any of the other combinations. No, this is the only one where it works. And it's something familiar to you. And with this grouping, you can do it. The others you can't. Try and figure it out. And I'm just going to answer it now. So, you want to know the answer? Here. Well, suppose I do this instead. That is, remember we're calling calling function with 1, 2, and 3. Now I've just added some more argument. Now here's the call code. Okay. So the caller knows he pushed 6 things on, so he cleans it up. No problem. Now here's the stack at the point of entry. So that for who, you'll notice that from this point down, it's exactly the same. Nothing changed. And the leave code is exactly the same because he doesn't need to know how much to clean up. So that is, you can push as much as you like on the stack, and it makes no difference for foo. And that gives you the ability to do this. You can have these functions where you can have a variable number of arguments, maybe 10, 15, 30, doesn't matter. And that enables you to have a function like printf. And the idea with printf is it doesn't know how many arguments are coming, but it has a little math here that sort of tells it the layout of what's on the stack. So that's what the format part is for. And like for instance, %s tells it there's a pointer. The first thing it's going to see is a pointer. Then it's going to see an integer. Then it's going to see a float, and so on and so forth. And then it just goes through the string, parsing through the string, and extracting the information from the stack. And now you got printf. Okay. So that's it for that. Now I want to get on. Maybe that's probably. I'll just leave it there, and then the next one, finally, we'll get on to the DOS way of reading the keyboard. All right. So.